Good morning, everyone. My name is Mohammad Nawed Ashraf, and today I'll discuss synthesis, processing, and fabrication methods based on Chapter 4 of AR Waste book Solid State. So, in this discussion, I will explain solid state reaction methods, nucleation and growth, epitaxy and topotoxy, practical consideration and examples, combustion synthesis, mechanosynthesis, and finally chemi-DOS method including various sol gel zeolites, hydrothermal and solvothermal processes. Solid state reaction shake and bake method. I will begin with the traditional high temperature solid state reaction method. This is the oldest, simplest and still most widely used method to produce inorganic solids. In this method, powdered reactants are mixed thoroughly, sometimes passed into pellets and heated in a furnace for long periods. Because it requires little sophistication, it is something humorously called shake and bake method or beat and heat method. However, the limitation is that mixing of reactants is only good at the micrometer scale but poor at the atomic level. So even if powders look well mixed, the atoms of different elements are far apart. To achieve atomic level mixing, the reaction depends entirely on slow solid state diffusion or occasionally on solid or liquid phase transport when volatile species form. A typical example used to illustrate the mechanism is the formation of spinel MgAl2O4 from MgO and Al2O3. Now let's look at the nucleation and growth in solid state reaction. Nucleation begins at the interfaces where MgO and Al2O3 grains touch. These contact points contain all the necessary ions and therefore a small product crystallizes or nuclei can form here. A nucleus is a very small stable region of the new phase, but it must reach a critical size, usually tens of atoms, to avoid dissolving or disintegrating. Nucleation is generally heterogeneous, that means nuclei form on surface or defects rather than randomly in the bulk. In the MgO Al2O3 system, nucleation can occur on both oxide surfaces, but it is easier on MgO because MgO and spinel have very similar oxygen sublattices. Both are based on closed pack layers with comparable cation arrangements. Once stable nuclei form, growth begins. Growth occurs by the diffusion of Mg2 plus and Al3 plus ions through the newly formed product layer. At first, the reaction is fast because the reactants are in direct contact, but as the spinal layer thickens, the grains lose direct contact and growth becomes diffusion limited, slowly down significantly. Here is the idealized reaction mixture composed of grains of MgO and Al2O3, and this diagram shows nucleation of MgAl2O4 spinel which is of A MgO and L2O3 is the B, and letters A, B, C refers to close packed layer of oxide ions. Now epitaxy and topotaxy. In many solid-state reactions, the product grows with a preferred crystallographic orientation. This brings us to epitaxy and topotaxy. Epitaxy refers to a two-dimensional crystallographic match across the interface. If the substrate and product have similar lattice spacing or symmetry in at least one plane, The nucleus aligns itself with the underlying structure. For example, MgAl2O4 nucleated on Al2O3 exhibits epitaxy because the structural similarity is limited to the interface layer, whereas topotaxy, however, is a three-dimensional structural relationship. It occurs when the product's oxygen and cation layers match with the parent structure in all three dimensions. MgO to MgAl2O4 is the topotactic because both have similar close-packed oxygen arrangements and similar cation ordering. These orientation relationships lower the activation energy needed for nucleation and promote smoother growth. This is the spinal product layer separating MgO and Al2O3 reactant diagram. Practical consideration in solid state reactions. Several practical factors must be considered to ensure successful solid state synthesis. First, the starting materials must be pure and correctly proportioned. They should be free from moisture and carbon dioxide contamination, especially materials like alkali metal oxide or carbonates. Second, fine grinding is essential. It increases the interfacial contact area, which directly accelerates the reaction. Third, choosing the correct container is extremely important. Some oxides react strongly with silica glass at high temperatures, therefore, platinum, alumina, or sometimes gold containers are used. Fourth is that the heating schedule must be carefully controlled. Often, reactions require repeated cycles of heating, grinding, and reheating to ensure completion. Controlled atmospheres, oxidizing inert or reducing may also be necessary depending on the material. These factors greatly affects whether a solid state reaction succeeds or fails. Example Li4SiO4. Li4SiO4 is used as a solid electrolyte in synthesis illustrate challenges in solid state chemistry. The reactants are Li2CO3 and SiO2. However, Li2CO3 melts around 720 degrees Celsius and can react with many crucible materials. It can also lose CO2 unpredictably. To handle this, the mixture is often heated in gold containers. Before the main reaction, Li2CO3 is pre-decomposed at around 650 degrees Celsius to Li2O, which reacts more radially. This avoids violent gas release and improves homogeneity. Also, another important example is YBA2Cu3O7 minus del, that is called YBCO superconductor. This is important because it is a 90K superconductor. Several difficulties arises. BaCO3 decomposes very slowly. CuO reacts with many crucibles. Oxygen content must be controlled preciously to obtain the superconducting phase. Solutions include using BaNO3 whole twice instead of BaCO3 to avoid decomposition issues, using pre-sintered YbCO pellets as substrate to avoid reaction with containers, and finally annealing the product in oxygen at around 350 degrees Celsius to achieve the correct oxygen stoichiometry. Combustion synthesis. Combustion synthesis is also known as self-propagating high-temperature synthesis (SHS). Uses very exothermic reactions that once ignited continue on their own. Temperature can reach around 3000 degrees Celsius within seconds. An example is the thermite reaction of Fe2O3 and Al to form molten iron and Al2O3. In solid state metathesis, one product is a volatile species like LiCl whose evaporation drives the reaction forward. An example is 5Li3N plus 3TaCl5 forms 3TaN plus 15LiCl plus N2. The gases released cause the formation of fine porous powders. Combustion methods are widely used to make nitrides, carbides, borides, and even carbon nanotubes. Mechanosynthesis. In mechanosynthesis, mechanical energy from ball milling is used to initiate chemical reactions. High energy impact create defects, break particles to the nanometer scale, and locally generate heat. Together, these effects are sufficient to trigger reactions even at room temperature. The products often have unique structures compared to conventional synthesis, metastable phases, nanocrystalline domains, and disordered regions. For example, Zn2SNO4 nanograins prepared by mechanosynthesis short inverse spinal cores but disordered outer layers. Mechanosynthesis is especially valuable for producing nanomaterials without high temperatures. Chemidose low temperature method. Chemidose means soft chemistry, referring to low temperature routes such as solution chemistry, sol gel processing, hydrothermal methods, and ion exchange reactions. These methods enable synthesis of metastable compounds, delicate frameworks, thin films, and materials that cannot survive high temperatures. Alkoxide sol gel method. In the alkoxide sol gel method, metal alkoxides such as SiOr whole 4 or AlOr whole 3 are dissolved in a solvent. Hydrolysis converts OR group to OHR, and condensation reaction form MOM linkages, creating a three-dimensional gel network. Hydrolysis example SiOr whole 4 plus H2O forms SiOr whole 3 OH plus ROH, and also condensation example SiOr whole 3 OH plus OH SiOr whole 3 forms SiOSi plus H2O. After drying and calcination, we obtain highly homogeneous oxide powders or coatings. Synthesis of MgAl2O4. For MgAl2O4, magnesium and aluminum alkoxides are mixed and hydrolyzed together. A mixed MgOl gel forms through condensation. After drying, heating at moderate temperatures converts it into spinel. Compared to the solid state route, the sol gel processes offers better homogeneity and lower sintering temperatures. Preparation of indium tin oxide and other coatings. Indium tin oxide ITO is widely used as a transparent electrodes in displays and energy control glass. Using sol gel method, indium and tin alkoxides are mixed into a precursor solution. The substrate is either dip coated or spin coated, forming a thin film. After controlled drying and heating, a transparent and adherent amorphous layer forms. Similarly, Ta2O4 films for capacitors and SiO2 TiO2 anti-reflective coating for solar cells can be prepared by this method. A major challenge is preventing cracks during the drying. Thick coating shrinks unevenly, so thin films are preferred. Sol gel using oxyhydroxides. Another sol gel route uses oxyhydroxide and colloidal chemistry by adjusting pH metal like aluminum from species such as Al3 plus, AlOH2 plus, AlOH whole twice plus, and AlOH whole 4 minus. Because aluminum is amphoteric, it dissolves in both acids and bases, but forms gelatinous AlOH whole thrice near neutral pH. These polymeric nanosized oxyhydroxide species link to form hydrous oxide gels. On heating, they convert to ceramic oxides. This approach is widely used for elements such as silicon, phosphorus, zinc, tin, and many transition metals. Synthesis of zeolites. Zeolites are porous aluminosilicate frameworks used as catalysts and molecular sieves. They are synthesized by hydrothermal crystallization of gel prepared from sodium aluminum hydroxide and Na2Si3O7 and NaOH. The gel forms at room temperature, then crystallizes at 25 to 175 degrees Celsius. Organic templates like alkyl ammonium ions determine the pore structure. After crystallization, the template is removed by heating at around 300 to 400 degrees Celsius, leaving open channels. Hydrothermal and solvothermal synthesis. In hydrothermal synthesis, reactions occur in water at high temperatures and pressures. Water acts as both solvent and pressure medium, enabling the formation of phases not stable at ambient conditions. Typical temperatures around 25 to 350 degrees Celsius with pressures of several millipascal. This method produces material like BaTiO3, Fe3O4, and alpha Al2O3. Solothermal synthesis is similar but uses organic solvents. These solvents provide different polarities and boiling points, giving precise control of particle morphology. Supercritical solvents promote rapid nucleation and growth of nanoparticles. Solvothermal methods are used to synthesize oxides, sulfides, phosphates, and even MOFs. This is the diagram of pressure temperature relation for water at constant volume, and this is the schematic of hydrothermal bomb used for crystal growth. So this was my presentation, and at the end, thank you all.